All right, let's look at one last vector application problem. So in this one, we have an 800-pound weight that's being suspended from two cables, as shown in the figure here. And we want to know what are the tensions in these two cables. Okay, so let's go ahead and think about all the different forces that are in play here. So we have this 800-pound weight. So we, of course, know that gravity is pulling down on this. I'll call that F sub g, that's my force of gravity, okay? And we know from previous example that the force of gravity is the same as the weight of the object. So that force downwards is 800 pounds. All right, now we also have the force in the cable on the left pulling up toward the ceiling. And then we also have the force in the cable on the right, okay? All right, so I'm going to call the left cable F1, and I'm going to call the right cable F2, okay? All right, so as far as the tension goes, okay, it asks us what is the tension in the two cables. The tension is essentially the magnitude of that force vector. So just to make it a little bit easier as far as our algebra goes, I am just going to say, I'm going to let F1 without the line over it. I'm just going to let that equal the tension in the left cable. And I am going to let F2, again without the arrow over top of it, be the tension in the right cable. Okay, so I'm just using this notation here in lieu of the magnitude bars, the absolute value bars, just because we're going to be putting these variables in several of our equations, and it's just going to get a little bit cumbersome if we're trying to use those magnitude bars inside of our equations and do algebra with them. So I'm just kind of using a shorthand notation in this one, but I just want to let you guys know what notation I am using here. Okay, so I'm going to go ahead and I'm just going to redraw this figure just so we can label it out a little more clearly. Okay, all right, so like I said, this is our F sub g. This is our F2 on the right, and this is our F1 on the left. Okay, so basically we just need to break down each of these forces into their horizontal and vertical components. So I'm going to go ahead and start with the cable on the left, which I've called F1. All right, so we have our horizontal component, which is pointing to the left. So I'm going to call that X1, and it's negative because it's left, so that'll be a negative X1. And then our vertical component is pointing up, so we'll call that Y1. And then if we break down the cable on the right, this is pointing right and up, so they're both positive. So I'll call my components X2 and Y2. All right, now as far as the angles go, the cable on the left had an angle of 35 degrees to the horizontal, so that is also going to be the same as this angle inside our triangle to the horizontal. So that's a 35-degree angle. And on the right-hand side, our angle to the horizontal is 50 degrees. Okay. All right, so now coming up with our vectors here. So let's start with the cable on the left. So x1, that's our adjacent side, that is going to be equal to f1 times the cosine of 35 degrees. And then y1 is going to be equal to f1 times the sine of 35 degrees. Okay, x is cosine, y is sine. And then putting that together, our f1 vector is going to be equal to, we said x1 was negative, so negative f1 cosine of 35 degrees in the I direction plus f1 sine of 35 degrees in the j direction. Okay, now let's jump over to our cable on the right. So x2, that's our horizontal component, is going to be equal to f2 cosine of 50 degrees. And then y2 is going to be equal to f2 sine of 50 degrees. So putting that together, our force vector is going to be f2 cosine of 50 degrees in the I direction plus f2 sine of 50 degrees in the j direction. Okay. All right, and then lastly, our force of gravity, that's pointing down, and it was an 800-pound weight. So that is going to be negative 800 in the j direction. Okay, so we now have all of our force vectors. Okay, so one thing to think about if we think about the physics of this situation, it says that this 800-pound weight is being suspended from these cables up here. So because this is just a stationary box being held in place by these cables, nothing is falling, nothing's swinging, nothing's breaking, okay? The forces in this system are all going to add up to 0. Okay, because if nothing's moving, there's no net force on the system. So that means that when we add up all of our forces, F1 plus F2 plus Fg, these have to add up to the 0 vector. All of our forces are going to add up to 0. Okay, so let's go ahead and write that out. So we'll have negative F1 cosine of 35 degrees in the I direction plus F1 sine of 35 degrees in the j direction plus F2 cosine of 50 degrees in the I direction plus F2 sine of 50 degrees in the j direction minus 800j is equal to the 0 vector, so 0I plus 0j. All right, well, another thing that we know is that when we add or subtract vectors, we do so component-wise. We combine like terms. So if we think about all of our horizontal components in this system, or all of our i's, we have the negative f1 cosine of 35, we have the f2 cosine of 50, and we have the 0 on the right-hand side. So putting those all together, we'll get one equation. I'm going to come up with a new equation for my horizontal components. Okay, so we would have negative f1 cosine of 35 degrees plus f2 cosine of 50 degrees is equal to 0. Okay, because of course when we add all of our I terms on the left, they have to equal the I terms on the right-hand side. So just worrying about the components, not the I piece of it, putting them together, we get this equation. Okay, so then our vertical components are all of our J's. And same thing, if we add up all three of our vertical components on the left-hand side, they have to equal the 0 on the right-hand side. So that gives us another equation. Okay, so we would have f1 sine of 35 degrees plus f2 sine of 50 degrees minus 800 is equal to 0. Okay. All right, so now with these two equations for the horizontal and vertical components, we essentially have a 2x2 system of linear equations. We have two equations, we have two unknowns, and we just need to solve it out. So the way that we can do this is using substitution. So I'm going to go ahead and take my equation for my horizontal components, and I'm going to solve it for F2. So if we isolate our F2 in here, we would get F2 is equal to F1 cosine of 35 degrees divided by the cosine of 50 degrees. Okay, now I'm going to go ahead then and take this and substitute it in for the F2 in my other equation. Okay, so we would have F1 sine of 35 degrees plus, okay, so now I'm substituting in place of my F2, I'm putting in F1 cosine of 35 degrees divided by the cosine of 50 degrees. Okay, so that was my substitution right there. And then that's still times the sine of 50 degrees. And I'm going to go ahead and add this 800 over to the other side. So it'll be equal to 800. Okay. All right, so now we're solving for F1. So I'm going to go ahead and factor my F1 out of this equation. So that would give us sine of 35 degrees plus the cosine of 35 degrees times the sine of 50 degrees all over the cosine of 50 degrees. That's all multiplied by the F1, and that's equal to 800. Okay, so then solving for F1, we just need to divide by this whole thing in parentheses. So we'll have F1 is equal to 800, and then divided by that whole term, sine of 35 degrees plus the cosine of 35 degrees times the sine of 50 degrees all over the cosine of 50 degrees. Okay, all right, so finally, pull out your calculator, throw this in, and we will get F1 is equal to 516.19 pounds. So that is the force in the cable on the left-hand side. And then lastly, we want to solve for F2. So going back up to this equation right here for F2, we'll have F2 is equal to 516.19 times the cosine of 35 degrees all over the cosine of 50 degrees. And then plugging that into our calculator, we get 657.82 pounds is the tension in the cable on the right. Okay. All right, guys, so that is it for our vector applications. I've also posted some additional problems online, so you can feel free to go through those, and I've posted the solutions to them as well. So if you want some more practice, definitely take a look through those.